Welcome back to Math 332. Today we are going to look at chapter 2, which is going to be on determinants. And in this chapter, we are going to look at how we are going to compute the determinant of a 2 by 2 matrices, 3 by 3, 4 by 4, and general n by n. We're going to discuss their properties. And at the end, we are going to look at how we can use the determinant to derive invertibility criteria for a matrix, which means that we can characterize which matrix invertible just based on the value of its determinant. All right, so let's get right to it. So we have seen determinant before. If you recall that if you're given a matrix, a 2 by 2 matrix, which is matrix A right here, and you recall that in high school from a previous discussions that the inverse of this 2 by 2 matrix is easy. We have an explicit formula that looks like this to compute the A inverse, obviously provided that the AD minus BC is not equal to 0. Otherwise, you will have division by 0, which doesn't make sense. So if you recall, we call this number AD minus BC as the determinant of the matrix A. So there are two different ways to write determinant. You can write determinant like this. You can also write determinant like this. We're going to use these two different notations throughout these discussions. So sometimes I will write this, sometimes I will write this. And usually from the context of the discussions, you will know what this notation means. All right, whether or not this is definitely not the absolute value of a matrix, which doesn't make any sense, right? So every time you see something like that, you have to know that's the determinant. And in fact, remember that one of the main things that we want to talk about in this chapter is the criteria for invertibility of a matrix. And from here, we already have that. Remember, for a 2 by 2 matrix, we know that the 2 by 2 matrix can only have an inverse if this term AD minus BC is not 0. So we can say that if the determinant of a 2 by 2 matrix is not equal to 0, the matrix A is invertible, because you can verify that if AD minus BC, if it's not equal to 0, these terms here, 1 over AD minus BC, multiply this matrix, okay, D and A minus B minus C, if you multiply with A, B, C, D, you will see that that will give you the identity matrix. So, so for 2 by 2 matrix, we know that if this AD minus BC is not equal to 0, the matrix is invertible. The question now is, can we extend this idea, these conclusions to 3 by 3 matrices, 4 by 4 matrices, and in general n by n matrices? Now, the answer is yes. We can use determinant to set up a criteria for determining whether or not a matrix is invertible. And we'll do it at the end of this discussions. But right now, we have an immediate problem, which is we know how to compute the determinant for the 2 by 2 matrix. But how do you compute the determinant of a 3 by 3 matrix, 4 by 4 matrix, and general n by n matrices? So in order to look at that, we'll have to look at several definitions. So let's look at the first definition, which says that if your A is a square matrix. By the way, all the matrices that we're going to talk about today, and every time we talk about the concept of determinants, the matrices involved are all going to be square matrices. Okay, if it is a rectangular matrices, we will not be able to talk about inverse. We will not be able to talk about the determinant. So if you have a matrix A, which is given here, so remember this is how we label their entries. A11, A12, A13, so on and so forth. So for each of the entries here, so for, say, for example, A11, so let's say in general Aij, we can associate a value to that entry, which is called the minor. So if A is a square matrix, the minor of this entry, denoted like this, is defined to be the determinant of the submatrix that remains after the I row and the j column are deleted from A. Which means that, let's say we are looking at A11 and we want to look at what is the minor of this entry's A11. Obviously, we denote it as M11. What we do is that we took away the first row, we delete the first row, and then we delete the first column, and then you will have a smaller matrix, which we call submatrix. Okay, so if you compute the determinant of this smaller matrix, okay, and then if you get the answers, that answer is called the minor, corresponds to these entries A11. So for example, let's say we take A23. So we want to determine what is the minor of A23. So you throw away the second row and throw away the third column of this original matrix. Then you get a submatrix. This is a submatrix. Okay, so this is a submatrix. A submatrix will look like this. Okay, so you have a smaller matrix. This is a submatrix. And if you can determine, we already know for a 2 by 2 matrix, so we can compute a determinant, which is this multiply this minus this multiply this. So if you compute the determinant of these smaller matrices, the answer is going to be given as this number, which you call minor M23. Okay, obviously this is the index to determine the locations, and then this is actually a value, a number. Okay, so every terms, every entries of a matrix will have a minor, okay, corresponds to it. So that's the notation minor. So for Aij, you will have Mij. Now, so if you assign, okay, if you assign a sign, yeah, terminology, to this Mij, which is that every time you have Mij, you have to determine whether this Mij you're going to assign a positive value to it or a negative value to it. And precisely the if you assign the positive and negative to the minor according to this formula. So if you have if your row is, if you are on an I row and j column, then you assign this negative value or positive values depending on this formulas. Then this whole thing here is known as the cofactor for these entries Aij. Okay, so cofactor of the entries Aij is the minor of the entries Aij multiplied either a positive or negative depending on their positions. So this is just terminology right now. This is defining what minor of entries Aij and the cofactor of the entries Aij means. So let's look at the example, computational example, so that you will be clear. Okay, so now you have a matrix A, which is given here. So for each entries, let's say we are looking at the A11 positions. So what are the minors? So you cross away this one, you cross away this one. So the minor is the determinant of the smaller submatrix. We know how to compute the determinant of a 2 by 2 matrix, which is taking this and this and multiply, which is 5 times 9, and then subtract, always subtract, and then multiply these two terms that's off diagonal. So this is going to be 8 times 6. So you will have 45 minus O is 48. So you have the value -3. So this is the minor of this position A11 for this entry A11. How about the cofactors? So for cofactor, you will have to put in this sign. Okay, put in this sign here. And the power here will be the I row and the j position. So it's going to be 1 and 1, which means that you are actually assigning something that is -1 to a power of 2, which is a positive number. So you get back -3. So in this case, your minor M11 and your cofactor C11 are both the same. Okay, -3 and -3. Okay, so let's look at another example. So let's say you are looking at the minor of that entries A23. So second row and third column, So you're looking at these terms. So for the minor, you will have to throw away this row and then this column, and then you will have to look at the determinant of this smaller matrix, smaller submatrix, as you can see, 1, 2, 7, and 8. So if you compute a determinant, which is this multiply this, subtract away the product of these two, so you get -6. Now that's the minor. That's the minor of the entries, the position A23. And how about the cofactors? So for the cofactors, is going to be the minor, okay? But then on top, in front of it, you will have to multiply a sign. It could be positive or negative, depending on the positions. So how do we determine the positions? We'll have to look at the sum of the row and the column. So in this case, the sum and the column add up to be 5. So you will have to take -1 raised to the power of 5, which will give you a negative values. So because your minor is already negative and the sign is negative, so negative multiply this negative will give you a positive numbers, and that is your cofactor for this positions A23. So you can see here the minor and the cofactor now differ by a sign, right? So they are not the same anymore. The minor is -6, the cofactor is 6. So that is the meaning of minor and cofactor. All right. So okay, so we can take a shortcut in terms of the sign, because if sign is just depending on the position I plus j, so if you look at this position, which is 1, 1, so you know that this thing is always positive because 1, 1, this power is 2. So this position is 1, 2. So 1 plus 2 is 3, is odd. So odd, at negative 1 raised to an odd power, so it's negative. And this position here is going to be 1, 3. So this thing add up together will be 4, which is even power. Negative 1 raised to an even power will be positive. So you can predetermine the sign for the minor. Then you can get cofactors. So for 3 by 3 matrices, you have like plus, minus, plus, minus, plus, minus, plus, minus, plus. This is one single way, easy way to determine the sign for the minor so that you multiply them together to get cofactors. All right, so why are we doing all this? You will know in a minute. Okay, so that's just basically the definitions and the notations for minor and cofactor. Now, all right, so let's look at the theorem 2.1.1, which says that if you have a matrix A n by n, obviously, because it has to be square, then regardless of which row or which column is chosen, the number obtained by multiplying the entries of the row or the column of the corresponding cofactor and adding the resulting products is always the same. So what it says is that once you define minor and cofactor, and then if you do this, okay, and then if you do this, so for example, let's look at this number here. Okay, so let's say you look at 1. All right, so you have 1. If you do this, 1 multiply the cofactor of this position, C11, plus the entries here, which is 2, multiply the cofactor of this position, 1, 2, plus 3, okay? And then the 3 is this 3, multiply the cofactor of this position, 1, 3. You will get a numbers. That number, let us call x, okay? All right, so let's do that for something else. Let's say we take this column. So we are taking the 2, okay? And then we multiply the cofactor. The C here stands for cofactor though, not the column. So we will have 2, 1. That's the position. Sorry, 1, 2. First row and second column. And then you plus the 5. It means you take the numbers and then multiply their cofactor. The cofactor though, not the minor, which means the sign has to be taken into account. So so this is going to be your 2. This is going to be entry second row and then second column is 2, 2. And then 8, you take the 8. And then you multiply the cofactor of these positions, which is 3, 2. The theorem says that it will going to be x. Same answer as this one, the same value x. If x is confusing, if you think x as a variable and unknown, let's say we give it a number. Let's say we give it some other notation. Let's say we call it alpha. Okay, so this 2 alpha is the same alpha. So it doesn't matter which row you do it. Like last time we do it on this row. Also, you can do it on the column. We do it on this column. Also, if you multiply the cofactor of a position together with the entries of the position and do the sum like this, that theorem says that you always get the same numbers. Okay, so that's what the theorem 2.1.1 say. So what it says is that if you have a square matrix, okay, and it say regardless of which row and which column is chosen, the number obtained by multiplying the entry. So you have to multiply the entries in that row and column by the corresponding cofactor, multiplying the entry. So it's not just the cofactor, but the entries. Okay, the entries with the cofactors, the entries with the cofactor, the entries with cofactors, entry with the cofactor, entries with a cofactor, entries with a cofactor. Then you always get the same values. Now, we don't prove this theorem here because, in fact, the concept of determinants can be, it all depends on how you want to start the definitions. Because if you look at some book, they will define the determinant as a sign elementary product and all that. We're not going to do all that kind of proof here. I'm just going to point you to these observations, which is given by this theorem, saying that if you do all this mysteriously, somehow, okay, we're not going to look at why right now, actually in this course, but somehow the theorem says that if you do all this, okay, you always get the same number. And because of that, we can define all this computation here and this number here, right? We can define the number we obtained by going through all this computation as the determinant of a matrix. And then that particular concept will not be, it's going to be well defined because you always get the same number. So that is what we're going to do here. That's the definitions 2 given in the book as definition 2 on page 108. 108. So what it says is that if you have A, n by n matrix, the number obtained by multiplying the entries in any row or any column of A by the corresponding cofactor and adding the resulting product is called the determinant of A. And the sum and the sums themselves are called a cofactor expansion. That is here. That is what I'm saying here. That's the thing that we did, which means that the things that we did, okay, this number now is called the determinant of the matrix A. This number now, which is the same number, okay, as this number, this is also now is going to call the determinant of A. And this whole thing here is called the cofactor expansion. It's an expansion of something, right? You take something plus something, take something plus something, so it's an expansion of something. That's some expansion is called cofactor expansion. The theorem guarantee that no matter which row and which column you start by doing all this thing, because you're going to get the same answers according to this theorem, which means that you're going to get the same determinant. Determinant is defined, well defined. If you have a concept of computing something, and then if you have computed using the first method, you get number 5. You compute it using the second method, you get the number 7. Then that concept is not well defined. But we don't have this problem. We always get the same number no matter what you do. So that number now is called the determinant of that matrix. So for computing the determinant for any square matrix, we have this as our definition. That's what we mean when we say determinant now. So determinant is nothing but this particular expansion. Okay, you can expand along the j column, or you can expand along a particular I column. It's going to be the same. So for example, that's a matrix 4 by 4 matrix. How do we compute the determinant of A? Well, let's pick a row and let's expand on the row. Let's take the third row. So if you wanted to find the determinant of that matrix using the cofactor expansions on the third row, what you're going to do is you take A31, multiply the cofactor 31, plus A32, multiply the cofactor 32, and then plus A33, multiply the cofactor 33, plus A34, multiply the cofactor 34. Then you will get a number, because all the cofactors are just a number, because determinant of a matrix is a number, and all these entries here are numbers. So you get a value, you get a real numbers, and that number is called the determinant of A. So we are expanding along the third row. So when you see that we expand along the third row, the I here is going to be 3. So you can see that this is 3, this is 3, this is 3. They are always 3. This is always 3. And then things that is changing is the column, which is from column 1 to column 2 to all the way to column n. In our case, you can see that we have column 1, and then we move to column 2, we move to column 3, we move to column 4. But the row position is always 3. So this 3 is always fixed, and then you can see column changes from 1 to 2, and then to 3, okay, and then to 4. So this is called the cofactor expansions. This is called the cofactor expansions for this matrix A along the third row. Now you can expand along any row. In fact, you can also expand along any column. So let's pick a column. Let's say we are going to do look at the fourth column. So if you take A14 multiply C14 plus A24 multiply C24 plus A34 multiply C34 plus A44 multiply C44, you will get values. That value is called the determinant of this matrix A, and we say that this is the cofactor expansions along the column number 4. So this is cofactor expansion along the fourth column. So in this case, you can see that J is now 4. So all the J will be 4, all the J will be 4. So all this J here will be 4, 4, 4. It's not going to change because we are going to be on that column, fourth column. But then when you do these expansions, you can see that the row changes, 1, 2, 3, 4. So you can see row changes from 1 to 2 to 3 to 4. But then we are going to be on the fourth column, so the J will not change, but the row indexes here, the row indices here will change. So this is known as the cofactor expansions for this matrix A along the fourth column. Now the theorem says that no matter what you do, you're going to get the same number. That's the reason why that you can expand along a particular column, either this one, you can do it on this also, you can do it on this, or you can do it on this. If you don't do the column, you can do the row. You can do it on this row. You can do it on this row, so on and so forth. They're all going to give you the same number, and then that same unique number is referred to as the determinant of this matrix A. So now we have a way to compute the determinant of any n by n square matrices. Okay, we just need to do expansion, pick a row or pick a column. We usually do row, but you don't have to. You can do the column. So pick a row or pick a column and start doing that expansions. For example, so say you are asked to find the determinant of this matrix. So this is inconsistent with this using this terminology, this notation, determinant of a matrix A. So instead of writing this, we're writing this here. So obviously this is the matrix A, and you are asked to find what is that value. What is the value, which is what we call determinant of this matrix. So let's pick a row. Because there's a 0, so I'm going to pick the first row because it's easy. When you have a 0, I don't even have to compute this. I simplify our computation a little bit. So sometimes this is what drives you on which row or which column to pick. So in this case, let's just pick this first row. So we take a 3. All right. So we take a 3, and we need to figure out the cofactor. But the cofactor for this positions is the same as the minor. Remember that we have the sign plus, minus, plus, minus, plus, minus, plus, minus, plus. So if you're looking at these positions, the minor and the cofactor have the same value. So that's what you can see here. But here, you will have a minus sign that is coming from the -1 to the power of I plus j. And in these positions, the I plus j is actually going to be an odd power. That's the reason why you still have that. And then, so once you have that, that's the minor, which is throw away this one, and just look at this submatrix, which is, as you can see here, and you try to find the determinant. Now, obviously, this thing works because we know the determinant of 2 by 2 matrix already, so we can compute this. And as I said before, because of the 0 here, you don't have to do anything on that computation right here. So if you do this computation, this is called the cofactor expansion along the first row. You get the answers, -1. Now, let's say it's the same matrix. Let's say we are now looking at the first column. So instead of doing the first row, let's say we do the first column. It's not a very wise choice because it computationally is harder because every terms here they are non-zero, so you do have to compute all that. That's fine, just for computational purposes. You can check that. So by the way, the sign have to be careful. So this is plus, minus, plus, minus, plus, minus, plus, minus, plus. So that all these terms here is the minor. But if you want to look at what, but we're not talking about the minor, we're talking about the cofactor. So that's the cofactor, that's the cofactor, that's the cofactor. So you do have to pay attention to the sign, because if you get a sign wrong, you don't get a determinant. So this whole thing is called a cofactor. This thing is called a minor, right? And this is the 5 coming from here. So you take the 3. So you take the 3 right here, and then looking at this entire cofactor, multiply that, plus the -2. This is the cofactor for that number. This is the 5, and this is the cofactor for that expressions. For our matrix here. So if you do all that computations, you will get also -1. And this is known as the cofactor expansions along the first column. This is the cofactor expansion along the first row, and you should get the same number. If you don't get the same number, you make a mistake. All right, so that is a 4 by 4 matrix, and that's how we compute it. So suppose you are 3 by 3 matrix, I'm sorry. That's another example of how to compute the determinant of a 4 by 4 matrix. Now, you can do it on any row and any column that you want. You can pick this one, but I'm not going to do that because it's going to be computationally more complicated. I would like to do it on the first row because I have 2, 0 here. Okay, so if you have 0 and then cofactor of 1, 2, that's going to be 0, 0. And then the cofactor 1, 3, that's going to be 0. So it's going to simplify our computation a lot if you pick the first row. So if you look at this first row and we do that computations, and you will see that you will have to take this value, okay, and then the minor will be throw away this one. So it's a 3 by 3 matrix, submatrix. You will have to find the determinant. So in this case, you will actually have to compute this. And then, so how do you actually do that? So how do you compute the determinant of this 3 by 3 matrix? Well, you follow what you know from before. You still have to go through the first row. See, I'm picking the first row. Did I pick the first row? No, I am a little bit lazy here. I don't want to pick the first row. I can pick this second column. So think of it as this is your new matrix and apply what you know from before. So determinant of a 3 by 3 matrix. This is a determinant of a 3 by 3 matrix. We talked about that before. You can do row cofactor expansion along here, along here, along here, or do the column versions, which is along here, along here, along here. And I am going to look at my second row because there are 2, 0. So I am going to expand along the second column. So I have the -2, and this is, by the way, just +1. So I have the -2, and then I throw away this one and this one. I have the submatrix. I'm computing the determinant of the submatrix to get -6. Now, if you don't want to do that, you can actually pick something here or something here. I would suggest that you should do all these computations to see whether or not you get -6, and you should. So the way, so as you can see, the way that we talk about the determinant, you will kind of have to know the smaller cases first. So you can see that for 4 by 4, your minor is actually 3 by 3. So how do you compute minor of 3 by 3? Minor is the determinant, right? So you actually have to go back and know how to compute the determinant of a 3 by 3 matrix. And when you compute a determinant of a 3 by 3 matrix, you will have to run into the determinant of a 2 by 2 matrix. So even though we know how to compute it, but for big matrices, this might be complicated. So let me say that again. So if you are doing a 5 by 5 matrix, if you try to, A is 5 by 5, and you try to compute the determinant of a 5 by 5 matrix, okay, then you will have to run into how to compute a determinant of a 4 by 4. Okay, and for the determinant of a 4 by 4, when you are computing the determinant of 4 by 4, you will have to do the determinant of a 3 by 3. And we compute the determinant of a 3 by 3, you will have to do determinant of a 2 by 2. You have no choice because that's how we define the cofactor expansion, because for every minor, it is the determinant of a submatrix. So inside that, have another submatrix, you will have to figure out how to compute the determinant, so on and so forth. So even though we have a very nice way of saying how to compute the determinant using the cofactor expansions, I just want to point that out, which is this thing here, cofactor expansions. We have a very easy way of writing this, but the cofactors, all these cofactors might be a little bit complicated to compute if your matrices is big. All right, so this is how we do cofactor expansions, and there are several cases here where you can find out that these are special matrices, and for these special matrices, which is upper triangular matrix, lower triangular matrix. What is upper triangular matrix? So this is called the lower triangular matrix, okay? This is called the upper triangular matrix, and obviously this is called the diagonal matrix, right? So lower triangular matrix will have all the non-zero entries on the lower part. As you can see, upper triangular means this. I think once I point this thing out, you should be able to see why lower and upper. And then we have diagonal matrix. Now, these are all special matrices. You can actually try to do cofactor expansion on this, and you will see that the determinant is nothing but the product of the one that is on the diagonal. So let's say, obviously there are so many zeros. So obviously if I want to do cofactor expansion, I'm not going to do it on this row. So I'm going to do it on the first row. So I have A11. And then I throw away this one and throw away this one. So I have to compute the submatrix. I don't have to go through all this because they're all 0. So I will have to compute the determinant of the submatrix. So I'm going to take this entry again. So I have A22, and then we'll have to compute the determinant of a 2 by 2 matrix here, which gives you this. So as you can see, this is going to be, you're going to be able to extend all this to n by n matrices. And it's still true that for the lower triangular matrix, the determinant is nothing but the product of the entries that is on the diagonal. Same thing here, okay? You should try to at least do this cofactor expansions on the first row, and also the cofactor expansion on the first row to see that we do have that, okay? And obviously for the diagonal matrix as well. So take this one, okay, find the minor is going to be this, and to compute the minor, we'll take A22 and then throw away this one, and second row and the second column, and then we'll have to find the minor of this, which is a 2 by 2 matrix, which we know is this multiply this, and then minus the product of that 2, which is 0. So you can see is that. So in fact, if you have a lower triangular matrix or upper triangular matrix and the diagonal matrix, the computation for determinant is going to be a piece of cake. All right, just that. All right, so I will pause right here for the first part of the video. So the first part of the video is nothing but the procedures. It's basically telling you the procedure of how to compute the determinant of a matrix, any square matrices, by invoking the idea of a minor and the idea of a cofactor. So what is minor and what is cofactors is all given here from the definitions. The theorem says that no matter what you do, all this computation here, all this thing is going to give you the same number. We call that number determinant of a matrix, so on and so forth. And you have seen how you actually apply that to compute determinant of a 3x3 and 4x4 matrices. Now, the second part of the video is going to be a little bit more theoretical, and we are going to do some proof, and at the end, try to show you the criteria of determinant to investigate or to verify, to find out whether or not a matrix is invertible or not by simply looking at the value of the determinant. That will be in the second part of the video, and I will see you there.